Okay, so the next talk is Konstantinos Meichanetzidis, who will talk about joint work with Kock, Felice, Toumi, Gogioso, and Chiappori on quantum natural language processing. Please go ahead.
Thank you, Joachim, and thanks to the organizers, of course, for organizing this very nice conference online. And thanks for accepting this presentation. This is a work that was presented at QPL 2020 earlier this summer in June. So it's about basically taking the framework that Martha introduced, DiscoCut, and seeing what we can do about plugging this stuff on NISQ devices, that is noisy, intermediate scale quantum devices that are available today, like the ones that IBM Quantum Experience provides. So let's start from Lambeck's book title, which is From Word to Sentence, and I extended as the initial motivation for this talk. So this talk is about categorically going from word to sentence and then to diagram, as Bob, Bernush, and Steve did in the 2010 paper. And this talk is about extending the slogan to say to quantum circuit to NISQ device. And this is the paper I'm going to talk about. We think of pregroup grammar as a free category whose objects are pregroup types. So there's a set of basic types in here, like N, S, stuff like that, like Martha showed in the previous talk. And then this Z is an integer that comes with it, which is the order of its adjoint. So a type to the -2 is like twice right adjoint. Type to the 3 is an adjoint, right adjoint of order 3. And type to the 0, sometimes I will not put the 0, is basically the type naked. And there is a special type, always the sentence type. And you will see its role. And basically this category is generated by these diagrams. So the morphisms are such that words are mapped to states. So there is no input here. And a word is this triangular box. And then the wire dangling below it, the output is its type that is assigned by the pregroup grammar. So there is basically a dictionary, which is a relation that assigns to words in the vocabulary, V, some product of pregroup types. PB is the free generated product of types. And also the grammar reductions are generated by these cups, these morphisms. Note, my diagrams always go downwards. So these morphisms have input 2 types. And if the adjoint order is such that the left one is one less than the right one, then they annihilate, or they're joined by a cup. So these are the cups that grammar reductions are composed of. So here's an example. So the parser will select some pregroup type products for every word from the dictionary. That is basically the relation that I said before. And if we have a grammatical sentence like this one, Bugs, Trolls, Poor, Elmer, and Bugs and Elmer are nouns, Trolls is a transitive verb, and Poor is an adjective, and they're given these types here, then the parsing is done by, the grammatical reduction is done by these cups. And we see that all of the N types annihilate and only the S type remains, right? So now this sentence we say is grammatical because this happens. It belongs to the language generated by this grammar category. So here I use DiscoPy, the library created by Alexis and Giovanni, whose paper you can find here, and GitHub repo here. So I used DiscoPy, and I used this toy vocabulary to randomly generate some sentences from the Lebowski universe. So you see we can get all the diagrams out and all of these grammatical sentences because the only wire that dangles down is the S wire. So now these diagrams, they were basically encoding the grammar. So DiscoCut, as Martha said before, is the model that was introduced by Bob, Marnoush, and Steve. And the idea is that you take these diagrams and you interpret them with a functor to some meaning category, which more or less like shares the same structure. So they use the compact close category of finite vector spaces originally. And the idea is, that the grammar is a skeleton and the meaning is the meat that you put on the diagrams. So another way to see it, and I've seen Dimitri Kartsaklis say it like that in some of his papers, and Bob likes to think of it like this. So the word meanings basically flow through the piping of the grammar, and then the flow is such that the sentence wire spits out, the sentence pipe is spits out the meaning of the whole sentence. So the whole thing is compositional like this. So because this talk is about quantum, I'll first start talking about the work by Zeng and Coecke, which was a way to say, well, look, these diagrams look very much like the ones of CPM. No, not CPM, sorry, CQM, Categorical Quantum Mechanics. So basically the idea is you interpret the diagrams in F-Hilb, like Martha mentioned before. So the idea is that these are now quantum states, and these cups are entangled effects, maximally entangled effects, or like Bell post-selections, whatever you want to call them. So the idea is that every type gets mapped to an exponentially large Hilbert space. So n becomes dn, where ns is the number of qubits that we assign to that space. And then what Will Zeng did is he assumed that if you have a quantum RAM where you can just efficiently prepare such states with in the Hilbert space, so it doesn't cost you that much to load these states on a quantum computer. You assume that you have fault tolerance, so full error corrected quantum computers. You don't have to worry about noise and stuff, which is not something that it's achievable today. And you assume something about the types for convenience, or you do some tricks like Martha showed before, where you copy the noun and so on to be able to deal with tensors. Then they said, oh, look, we can get a Grover-style quadratic speedup for the closest vector problem. That is, find the vector for class here, where class could be sports, art, politics, history, philosophy, and so on, to see which class, which concept this sentence would be closer to. Like Sterner rejects abstract spooks would be closer to philosophy or history rather than sports, for example. So our approach is NISQier, because we wanted to actually implement this thing with a very bad in quality quantum computers that we have today. Not to trash them, but they're all prototypes. So let's see what we can do with them. So basically, the idea is that similarly, we take the basic types, which taking products of them and adjoints would get assigned to words. Then taking types, we assign a number of qubits to each type. We take a functor like this to quantum circ, which is the category that is the category of quantum circuits, and is generated by diagrams that are basically quantum gates. And I will choose gates at family later. But for now, think of states being prepared from the old zeros. So these white blobs are ZX notation for the old zeros. And then this box would be a quantum circuit parameterized by some thetas. So this is a parameterized functor I'm talking about here. And it's preparing the state W for the word. So theta W would prepare the word W. We prepare the quantum states that correspond to that word. And accordingly, as I said, correspondingly, sorry, the Bell effects get mapped to these Bell state post selections here. So this is canonical, just to define a functor here. So what is in the box, right? So as I said, we can generate these boxes out of these smaller generators. So we can choose our gate set to generate diagrams in QCirc, this category. So one choice could be this C naught plus U3. So I can entangle qubits by C naughts into either direction, as in either qubit can be a control or target. And then I can use the Euler decomposition to say, look, I can put whatever phases I want on whatever qubit I want. Or I can choose IQP style generators, so I can build up my boxes, my circ theta boxes, out of Hadamard's and also control Z rotations. And because these things are universal gate sets, then basically I can consider that they are generators of QCirc, this category I'm choosing to encode my meanings into. So this is an example of a box generated by C naught plus U3 that prepares some state parameterized by these 10 parameters. And this is the IQP version, which was also used in this Nature paper by Voite, where they do machine learning with it, some supervised binary classification task. So take this sentence, physicist teleports quantum state, and I'm going to show you an animation basically of what I've said so far. So we parse, we replace the boxes with circuits, and then we get a circuit out. So now this thing is a valid circuit you could run, and you see it prepares a state. So the sentence meaning travels along this qubit. So I've made here the choice that every wire is 1 qubit, but I could make I could make larger scale choices. But for now, take this as a easy to understand example. So what can we do with this? So we can start learning a functor. So learning a functor is none other than learning these thetas of my parameterized circuits so that I can do some task. And here we chose a binary classification task where we have tuples of diagrams and labels, and these labels can be binary. So let's take them to be true and false for every sentence. So DI is a diagram, DI is some diagram in this corpus, say, and it belongs to the category of Pregroup diagrams generated by these grammatical diagrams, and then the labels come with it. And then the idea is that we should train all of our sentences that when we measure that sentence qubit that carries the meaning of the state, it should be 0 or 1 with high probability, and it should match the truth label. And this is basically the loop depicted in some sort of flow diagram where sentences go in, we get a circuit goes to the quantum computer estimates the label probability, then we take it to a classical machine, estimates the cost function or mismatch from the labels. If needed, we update the parameters. If we're not happy, we return to the quantum machine, and so on until we converge, right? If you converge, you're happy, and then you can form new sentences and see if they're true or not. And then you can say that you're doing question answering also, if you make your diagrams more complicated and your labels as well. So NISQ processors look like this. So you see the connectivity is a bit limited. So not every qubit can talk to any other qubit. So for this, we use a compiler called Ticket by CQC, which uses a ZX calculus in its, under the hood to do all these diagrammatic reshapes and basically map any circuit you give it to these architectures. And this has to be done optimally because the circuits cannot be too deep. And this is because they're noisy. We don't have error corrections. So we have a limited depth until the whole computation becomes pure noise. But I won't say much about this because this is a more theoretical talk about the functors that we take. But to do these things, to actually map to quantum processors, we have to do some tricks. So one trick that was also introduced in Zeng-Coecke, the original one, which was needed to retain the quantum advantage, was implemented and expanded on by Stefano and Nicolo, who have this company called Hashberg. And also Stefano is based in Oxford as a departmental lecturer. And the idea is that you take the sentence and you create a bipartite graph from it, where some states become effects. And this has to be as small in width as possible. And basically you convert states to effects by transposition, which in CQM, CQM will tell you it's 180-degree rotation. So this is what it looks like. And then if you choose to put circuits in it, you get a circuit like this. Another version to do some trick to make your circuit easier to work with is to autonomize and remove snakes. So you freely add caps, not caps with a U, but caps with an A, which is the upside down version of it. So basically, the idea is that you take a type like this that has left and right adjoints, and you replace it with some box that has only non-adjoint types in its input and output wires, but you supplement with caps like this cap here and this cap here to compensate for it. So when you remove the wires, like by using this reference, then you get something that looks more circuit-like. And this is, you can see more about this in Giovanni's talk later on language games. Make Ludwig here very happy. So I'll show you an animation for how this works. And if you choose IQP style Ansatz to fill your boxes, then the functor will look like this if you animate it. So to summarize and take you through the pipeline once again, you start with a corpus, which is a bunch of sentences. We have this informal arrow here, which is the parser. And I know parsing is non-trivial, as in assigning pregroup types, but for now we take it as an input to the whole pipeline. But I know it's non-trivial, and we're working on integrating this in classical means for now to the whole pipeline properly. Then, as I said, we have a diagram in the grammar category. We can reshape it and do the tricks that I showed you in the latest part of the talk. We get a new reshape diagrams, and then we fill the boxes with circuits, as my animation showed. And now we have a diagram in circ, as in a valid quantum circuit. And then the transpiler, which is again an informal arrow, because solving these optimization problems can get dirty. So I wasn't brave enough to put a formal arrow here. I'm putting this wiggled informal arrow, but remember that there is the ZX calculus working under the hood here. So it's kind of semi-informal. And then the transpiler or compiler will send it to a NISQ device. So this is more or less what we've done and what I wanted to present. Again, the diagrammatic theories that were presented here basically were, discocat, which is the grammar part, and also if you take a functor to some other category, you have the meaning part. Here we chose CQM for encoding our meanings and specifically quantum circuits. And the ZX calculus helps us to build our ansatz and reason about them, both classically, if we want to do a classical simulation, or quantumly if we want to do the compilation to a NISQ device. So we have all these diagrammatic theories helping us to do quantum natural language processing. I want to say that my research is supported by the Royal Commission for the Exhibition of 1851, and basically I'm based in Oxford, but also this work is done with a lot of collaboration with Cambridge Quantum Computing, and also it was basically sponsored by CQC. And okay, so for future work, I want to say that we're running experiments, see how it scales. It would be ideal to couple the parsing part with the meaning part, but maybe it's a more of a long-term goal for now. The experimental part is more of the essence. More tasks, more complicated, more NLP-like tasks would be good to explore. Incorporating density matrices like the ones that Martha showed that can model entailment, hyponymy, stuff like that. This would double basically our circuits, so our diagrams would be doubled by CPM, the CPM construction. Maybe we can get away without post-selecting if we do this, just by discarding some qubits, which is easier operationally, you just ignore them. And then also moving to larger text is a long-term goal. Like you can see this reference by Bob, which presents a very high-level overview. And finally, I want to shamelessly advertise a job to work on this stuff on a team based in Oxford. The job is together with CQC. And if anyone is interested, please contact Bob or me. So yeah, thank you.
Okay, thank you very much. So maybe we have time for a few short questions. I don't see any. Unfortunately, I don't have any myself, but I think it was a really nice talk. So that's
Can you
just
hear me?
Yes, Alex, please.
I have a question, but I can't raise my hand for some reason. My question is about density matrices. Do you think there's some way to implement density matrices just by sending stuff, say probabilistically, to the quantum computer? So you're not really doubling the amount of stuff the quantum computer is doing. You're just introducing the mixture kind of by doing one of a kind of an ensemble of circuits.
Yeah. Yeah, I don't see why not. So like simulating the probability distribution over the pure stuff, basically. That's what you're saying. Yes, I don't see why not. I need to, what I need to understand is more how you can do channels, like arbitrary channels like this. Yeah, maybe you can help me with this. Maybe we can talk about this. I haven't thought of it much. Of course, I've only thought of the naive, just double the thing. Just have a deeper circuit now, but it's more general because you can do density stuff. Yeah, a good idea. Thanks.
Okay, any more questions, comments?
There are some comments on the chat. So Giovanni says you can introduce mixture by discarding some qubits. So now we're relying a lot on post-selection, but if you open the literature and see people that map tensor networks to quantum circuits, then they just discard qubits to make odd arity tensors. Like if you have a 2-to-1 map, well, you discard one of the outputs of a unitary, and now it's a tensor with 3 legs instead of post-selecting on it, which is expensive. And in the end, we just optimize the parameters, and if it works for the task that we want to do, then we're happy. And if it works with a cheaper method, then we're even happier.
Okay, thanks. So let's thank Konstantinos again.
Thank you.